Welcome to a new series. This is more of an exploration series where we will discuss similarities between bubble formation, cavitation, and phenomena such as supernova, star formation, right down to the components of the atoms itself. Now, this is something that Jim Weninger has been interested in for a while, but there are many different aspects that must be considered. The surface tension and double layer episode I did was a result of one of the papers that Jim had been interested in. Now, what we would like to present here is an open discussion about where the similarities lie, but at this stage, it is just that, a discussion, which will hopefully help stimulate others to look further into this to see if it does indeed hold any merit. The first section of this will be a two-part discussion, and there may be follow-up videos discussing further details if there is indeed merit in this path. But for now, let's dive into that discussion.
Yeah, we're still going to be, see what the issue is. We're going to have to put a lot of things together that haven't been before. That they're all out there, and now can see them, but they haven't been either because they're still not fully accepted, or no one's bothered to put each of these things together. And then you start seeing a general picture come together first, and a lot of interesting details. Then, like if we were just starting back at the beginning, remember when we were talking about Z pinches?
Yeah.
That weird relationship between charged double layers, which that's all worked out. We know we've all got a good. You did a video on charged double layers, and you did one on Birkeland currents, and those are kind of like two things that we still treat even in the EU community. That kind of isolated. We have nice cylindrically symmetric Birkeland currents, and then we have these nice charged, stable and static charged double layers, but the interaction between the two, like what happens when a current goes through a double layer, which it must if we have two charged regions in space or two charged objects, they're going to be protected by double layers until a discharge or something equalizes them, and then they don't need the double layers. But the double layers are there first. But the whole balance is what's interesting. Like whether obviously if you have a current going through a double layer far from the current, you've just got the double layer. Inside the current, you can pretty much treat it like that Bessel function filament. But then that region in between, that's where you see the different dynamics, like between, like the local chimney with that nice torus around it is quite a bit different than a sunspot, where the sunspot material has kind of that flow, but it's still flattened into the plane of the sun, and it remains in the plane of the sun. So in other words, it's a different dynamic when the current dominates compared to when the double layer dominates. You get different behavior.
Yeah.
But that whole thing, that whole interaction, that's where you see all these weird different shapes, and you can without even treating it mathematically, you can just like imagine how you would get a torus of material around orthogonal to the filament. That means it's taking all the material out of the double layer and doing what it wants with it. The current itself dominates. Whereas if, like in a sunspot, where all you have is, if a current has a radial electric field and its own magnetic field, that might generate flow in the double layer, but it's not going to take material out of the double layer. It's more of an influence on the double layer rather than dominating the flow of plasma.
Right.
But that interaction is that even matters like in the bubbles, because remember when bubbles collapse, they form jets, but the interesting thing is they collapse towards a wall where the far side is approaching the wall even faster, and the jet forms inside the bubble to the wall, not from the outside.
The jet and the wall, because it's not hit the wall, it's on the approach to the wall. So it doesn't have to touch the wall. It's just that obviously there's a...
Right. It's not the wall. This is where all these pieces from different people, like Gerald Pollack at the one of the EU conferences when he did his thing on water, one of his presentations was pretty much on the focus on what the charged double layers that happen at the boundary, like between the wall, but it's double layers in the fluid, in the water, before you're even getting to the wall. There has to be a double layer there. And now you see the different dynamic in that if it really is the double layers in the bubble keeping it spherical, but there's a double layer close to the wall, then you'll already see that the influence and where one takes over compared to the other. And even the jet, if you look at that boundary between the spherical bubble, you treat that as double layers. Nice, plain double layers.
Yeah.
And then on the other side, we have a jet. That's a Birkeland current. And you've got the other extreme. But how do you take material in these nice double layers and turn it into the same material that's suddenly in a jet? That means that the double layers that dominated when the bubble was isolated from the double layers at the wall, they're pretty much separate. You've got the nice spherical shape.
Yeah.
But once you start an acceleration towards the wall, that's what happens is once you have enough of a flow of charge, you have the magnetic field between the charged material, and you know how you get a Birkeland current. Basically, you're taking the material that was in that spherical double layer and you're making it all flow together towards the wall, and then you get the Birkeland current that forms.
Yeah.
But you could see why it would start on the opposite side, because the bubble collapses towards the wall, so that the part that's accelerating most, the part that's flowing the fastest, is the far side of the bubble. So if you get those interacting magnetic fields, that's where you're going to get the formation. And then, see, that touches on a whole nother subject of how in the mythology, you know, how a planet, Venus, supposedly came out of a gas giant planet, and they still argue over which one that was. But that would make a lot more sense if you had a blob of something coming out, that it would work that way. That's not like gravitational spin-off from the boundary, and it's also not onion skin fissioning like they talked about in the early days of, you know, EU.
Yeah.
You could see how you might get a jet of material coming from the other side and now fully, you know, pretty much something shooting out on the side towards you.
Yeah. I think in order to frame this, because I think it's going to be very difficult for people to follow, so I think what we need to do is go back and set the scene as to why you became interested in this. What is it about bubbles that sort of sparks your interest?
Well, I mean, obviously, like the idea of like a hollow sun is. Then you've got the analogy there, and then the double layers at the surface of the sun and the double layer at the surface of bubbles. But I think it was really more the whole stage when you look at the formation and collapse, like where knowing that there's this stream of stars going down the local chimney, and right in the narrow part is where we see these clusters of stars. That makes sense with the bubble formation process. That's what you get, is bubbles forming in the lowest pressure from the fastest flow through the center of the venturi. But then that more fascinating, because I was always interested in like red giant stars, and it's the collapse phases. You know, the whole red giant stars show radial velocity pulsations. And then there was, when they collapse, we see these remnants with, you know, the jets, just like we get in bubble collapse. And then there's the super flash of light from a supernova, and you get that same flash from bubble. So there's like that mere segment. There's just the collapse of red giants compared to the collapse of bubbles. There's just too many details that are the same. And if you just focus on just those stages, it's like, to me, that's fascinating. And then you can go back and put together the formation and what happens in the jets and where these things form and all that kind of stuff.
So this is really sort of almost like a comparative analysis in terms of not necessarily the underlying, although in some sense it is to do with the underlying mechanics, but it is looking at the shapes of the stars, in particular the red giants, and the fact that you end up with these jets being shot off just before death, and then comparing those to bubble collapse. So this is cavitation. So there you have a bubble, it grows, so the bubble gets larger, and then all of a sudden it reaches a point where there is some imbalance, and then it very rapidly collapses, and boom. And of course, when you look at these images, you kind of think, well, that's, like you say, it's a bit like what we would describe as a supernova, particularly when we look at red giants. The idea that they swell and they expand, that there is a sudden contraction and then a sudden brightening event. But you also mentioned the fact that it would also account for repeated novas. Is that right?
Right, because just like bubbles give off a flash of light, if they're driven to expand and contract again, you can get a flash of light and then a rebound instead of a total collapse. You can get a rebound and another flash of light. And now there's observations of another. I should have had that link, but recently they discovered a supernova acting badly, basically because it doesn't just die; it gives off another pulse of light. So that would be the same kind of analogy. But the real key to understanding both is once you understand that the bubbles, what makes them spherical, is that double layer, and that we knew from way back in the 1920s that the sun had to have a double layer at the surface. And there's that open question on why the sun is so spherical. The answer just screams at you then, well, yeah, if bubbles are as spherical as they are because of the double layer, the sun has the double layer at the surface, then obviously that's what's going to make the sun so spherical compared to just a rotating blob of gas that should be oblate.
Yeah. And I think for me, what was interesting in the paper that you sent me is the fact that it has surface tension. So again, not only relating to what we see in water, but the fact that there is this tension that you can have in a double layer also explains why you can have a double layer that changes shape, why it can expand, and why you could suddenly get this contracting. Because if the forces change, then all of a sudden you could end up with a surface tension that massively increases, or it is that the stuff on the inside is massively changing pressure. So for me, that's another piece of this key. But I think to be clear for people who are sort of watching this is not necessarily that we're saying this is the solution. It's more that this is a link that we identify in terms of what we see in terms of stars and in terms of the behavior of certain types of plasma, and then what we see in terms of bubbles. And there has to be a link there. There has to be a reason why there are such similarities between the way bubbles collapse and what we see in those stellar objects. And it's really trying to find, I guess, other people who are interested in trying to figure out more of this. It's not that this is a complete solution. This is like a breadcrumb trail that I think you've identified and that I think will lead somewhere. I think this is quite an important bit of the puzzle to understanding how some of these things work. Because for me, one of the big questions around, when we look at the star formation is effectively what we have, if we look at the sun, is a bubble within a bubble. You have the plasma column, the central column that would be the central axis of that Birkeland current. And then we end up with a little pocket that is our heliopause. And then within that, there is a star, which, as you describe it, would be a bubble in itself. So you almost have the sort of an anti-bubble and a bubble within a plasma column, if that sort of makes sense.
Yes, yeah. The one thing with the reason I should have suspected that even sooner was the idea of the shells of material that are formed in a Birkeland current, that nothing is really forced to the center. Things are forced closer to the center, but nothing should be at the absolute center. It should all be in shells, so that means you should have a lower pressure region if all the material is being evacuated from the center of a Birkeland current.
So I think it might be useful to explain your reasoning there. So what was that sort of, for you, the leap that sort of explained that there can't be anything at the center?
Well, basically, if you look at how Birkeland convection works, you see how it sorts, like it'll sort ions, for example, by radius, but none of them should have, like if you look at, let's see, you might find a cross there, that one with the cross section. Yeah, right there.
This one.
Yeah, it shows you, unlike the earlier drawing that just kind of shows a general spectrum of stuff, that shows you that, for example, the iron is closer to the center, but the iron isn't in the center. That's the issue. There shouldn't be anything right there. We should have this, like we do on a large scale, like the local chimney. We have a wall of hydrogen around the outside. That's a good sign. But you should have that region where really nothing is in there. It should be sorted into those shells. So that's a good reason to suspect that it was the material being hollowed out from the center rather than all forced in. And that goes better with the idea of like a hollow sun as a bubble rather than all this material forced into the center. It would be, again, just like cavitation bubble formation. It's the lower pressure region, so the sun would expand out into the Birkeland current.
Which has always been my sort of question, is trying to understand that formation process and, you know, what causes that initial imbalance to form that, you know, sheath to separate it from the outside. And again, if you look at the way bubbles form and the nucleation process for even, you know, stick your finger in a fizzy drink and the way that the bubbles form, you know, they effectively appear to form out of nothing. And they clearly they don't, because they need a point from which the trapped gas in the drink then turns into a gas. So it's about, and again, that's why I thought was interesting in that paper. It is about state change and maintaining the difference between two different states across that membrane. Now, obviously, when we talk about plasma, then the state change isn't necessarily that it's solid or liquid. It's to do with the how ordered it is. Yeah, so you have something that is more ordered is segregated from something that is less ordered. Or it could be to do with charge as well. Obviously, you know, double layers form to separate charge. So that's kind of key to it as well. And I think that to me makes sense, the fact that you would start from the center and grow outwards like a bubble grows. But
right.
It's still the question remains in terms of, you know, how that process actually initiates. Because, again, if you look at a bubble forms at a nucleation point. So the question is in a and we're getting slightly off topic here, but what would be that nucleation point in a, you know, a constant source of plasma? You know, and it could just be that it is a speck of dust, some you know, part of the plasma which is slightly more positive than the other, because again, you know, it could be dust in there, positively charged or negatively charged. You know, I'm sort of speculating now.
Well, that, you know, again, if you're going to trust the mythology that in the past a planet turned into a star, then that would make sense too. That to treat a planet as basically an impurity in the fluid, you know, and you could see then how the bubble would form on, you know, around that.
Well, and use that word fluid, and I think that's another key to a lot of these things that we're looking at, is there is fluid dynamics that are involved in the process of cavitation that I don't think there is necessarily an equivalent in plasma at this stage. I guess in terms of the bullfire is an example of a bubble, because it's two different states of plasma, or two different charges of plasma.
That plasma fireball, I think, is probably the best example of what, if people need a visual of how a star could be a bubble, it would be like that with the same dynamic.
And just to be clear, it's not that you're saying that it's not an electric sun, because some people will probably look at this and go, is this then an alternative theory to how stars function? And I don't think that's what you're saying.
No, you'd still need the flow. Like, we'd still be talking about Birkeland currents, the flow, you know, flow of plasma, and obviously charged double layers, and you know, the difference in, like the plasma fireball thing, the difference in charge between that goes with the even Don Scott and Wal Thornhill, the way they're looking at the sun being charged, that makes sense with their model. So that, yes, it would be a positively charged sun compared to its environment.
Yeah.
But yeah, it's basically like just not leaving out any of the units. Like, the mainstream tends to ignore all the electrical parts of it, but the good old fashioned fluid flow, they do maybe too much with that magnetism and fluid flow, but we can't ignore that either. I mean, that is an important dynamic that has to go together.
Well, it's also an interesting thing now. You mentioned the water and easy water, This is maybe not the greatest one, but another way to look at the cavitation is, is there a way that we can explain, particularly when we look at the sonoluminescence, the fact that you get this spark event. Is there a way to look at those bubbles in terms of what might be going on in terms of that double layer and explaining that flash? Because correct me if I'm wrong, but I'm not sure that they can explain the flash of light being produced, can they?
No, that's still a bit of an open question. I mean, depending who you read, they have theories, but if you look into it, you know that's not quite that's not settled science in itself.
I'm just wondering whether it's one way to approach this is to look at the cavitation bubbles themselves and to try and explain or try and work out the dynamic of what might be happening from a double layer point of view, and whether we can explain the behavior that we see in water and then apply that to what we might see in stars. So the reverse, effectively. Yeah,
this is where you can start putting all these ideas that are independently known, like double layers at the fluid boundary, double layers at a bubble surface, how jets are structured. Those are all independent ideas that haven't been looked at together. And that's a good starting point for someone that's even just beginning to consider the dynamic. Is just ask that question. If bubbles have this charged double layer at their surface, and if the wall has a double layer, what happens when the bubble comes close to that double layer at the wall? And then
So just to be clear, because I guess a lot of people might not understand, what wall are you talking about? Because sure, in a bubble experiment, the wall is the container. So when you looked at red giants, can you explain in terms of that context what they mean by the wall from the red giant story, super red giant?
That's where the interesting thing with Betelgeuse approaching that wall of gas and dust. And Betelgeuse is one of the few stars that we know that looked like there were observations that showed it varying from this nice spherical shape. But that's what happens in cavitation bubbles too, is they remain spherical, but once they get close to that wall, they distort. So that's another piece of the dynamic that's.
So this is the image here that's Betelgeuse, and this is an actual image. So this is then the outer part of the heliopause for Betelgeuse, and that's the wall that they're referring to. This solid, right. There's a gap in between it, and then there's more of this gas which they think is going to crash into it. And they believe that when it does, that this front will compress inwards, which will trigger, I'm guessing, the collapse of the star and the supernova.
Right. Now, if in the future, if that star really does, if it obeys the same dynamics that a bubble does, we should see a jet from that star towards that wall.
So like this. Right. So this would be that wall of gas here. So we would expect to see a jet coming out and towards it, which is interesting because, one of the things, and this is, again, slightly off topic, that I kind of look at is there are some, and I need to dig them out, but there are some young stars that exhibit jets, but only jets out of one pole. And there are some pulsars that also show jets, but as far as we can see, they're only out of one pole. So that's, again, there isn't really a good reason as to why that would be. So this is an interesting possibility. Now, in the context of Betelgeuse here being part of a Birkeland current, and what would you think this wall would be in that context?
Well, if you wanted to use the analogy exactly, then that might be the boundary of the fluid, really, that Betelgeuse is in, and more like like the walls of the local chimney, a dense wall of neutral gas and dust, would be the wall of the plasma fluid in that scale.
Right. So this would be somewhere outside of here. So it's a change of density, really.
And even a state change there, really, because of, it's definitely a hot, sparse plasma inside that, and at the boundary, they see actual neutral gas and dust. That's you're talking plasma to gas, basically. That's
because there's this as well. This also sort of fascinates me. This concept. So this is the paper. Which we talked about before, because one of the things that I'm sort of very interested in is ring formation. And this is the idea that they applied an electric field to a spherical, it was an oil drop. And what they then discovered is it formed these bubbles that formed a ring around it. So it's not just, when we say looking at bubbles, it's not just the supernova that we're sort of explaining, but there are other features of bubbles that, like this experiment here, may well explain other phenomena as well, from ring formations to equatorial outflow. It's a broad subject, I guess, is what I'm trying to say.
Right.
And these are just some of the papers that you've kind of come across looking at bubbles, the dare I say mechanics of bubbles, fluid dynamics of bubbles. Oh, this was an interesting paper. This is again, this is looking at gas bubbles submerged in water and its implication particularly for plasma breakdown. And for me, it was the shapes. Again, what they're looking at is producing did they put an electric field across this? No, they levitated it, and there was a... Yes, there is a... I can't remember. Yes, there is electrodes. And it was the shapes that they were able to create in the liquid. And particularly, so there's our torus. This shape I find particularly interesting because we see that often. Again, there is a different reason, but when we look at planetary nebula, that's a very common shape, a Z-pinch sort of thing. Is that central bit being pinched, creating that structure? Weirdly square and sort of diamond structures. And again, there are images that we've looked at, in terms of gas flow and things that have these angular edges that are harder to explain. And yet here we see them in, these are just gas bubbles. Oh, the nucleus. Yes. Yeah, there are many different ways to go with this, I think. But I guess the question is, what do you want to do with this?
Well, yeah, there's so many areas to explore once you see that. Even if you just take it, just posit, what if the sun is like a bubble? What can we learn from one scale that'll help answer open questions on the other scale, and just look for even more correlations. To me, that's the short term. And then also jump down in scale yet again, because you're going to find that there's a few features of, like on the nuclear scale, that you're going to need to keep those double layers in mind again.
I hope you've enjoyed this initial discussion on bubbles and cavitation. In the next part, we will continue this discussion and explore the subatomic realm. Please let us know if you think that this field does indeed hold merit by hitting that like button and leaving a comment below. As always, be brave, be curious, the truth is waiting for us. Until next time.